In Part 3 of Lecture 3, we will discuss operating system organization. The operating system is supposed to be an interface between users and the hardware of the computer. But there are many jobs that must be done that are not built into the operating system itself, but that users really do not want to do themselves. These include a lot of systems-related tasks, such as creating, deleting, and copying files, getting status information such as time, date, available memory, and disk space. It includes programs such as text editors that create or modify files, compilers that translate them into machine language, and programs that send messages to other users in real time or by email. These are all examples of system programs. Probably the most important example of a systems program is the command interpreter, or shell, itself. In Unix, the user has the ability of using one of several different shells, including the classic Bourne shell, the C shell, the Korn shell, and the Born Again shell. In DOS or Windows, command.com is the command processor, which can be loaded like any other systems program. An operating system is an extremely complex program with many more procedures than most other software projects, and with so many more of its parts very heavily interrelated. While it is possible to build it without any consideration to structure, it would be a very big mistake. It was in the course of designing the OS 360 operating system that Fred Brooks learned all about the wrong ways of designing and building large software systems. His book, The Mythical Man Month, which was heavily inspired by this project, discusses all the pitfalls that are possible in implementing complex systems, and not providing a structure for it would be high on the list. There are 5 different structures that are commonly used in operating system design: a simple structure, a monolithic structure, a layered structure, virtual machines, and the client-server model. DOS is an example of an operating system that started out small and outgrew its original purpose. DOS was originally intended as a successor to the microcomputer operating system CP/M, which did little more than load programs and provide basic disk management and basic I/O. When Tim Patterson of Seattle Computer Products wrote the original version of 86-DOS, which was later renamed MS-DOS by Microsoft and PC-DOS by IBM, he never intended it as an operating system for larger 32-bit computers attached to local area networks running graphical user interfaces such as Windows. This became possible due to changes in version 2 of DOS. With version 2, Microsoft added features inspired by Unix, such as a hierarchical file system, installable device drivers, and print spooling. A close look at DOS's structure shows some of its origins in CP/M, an operating system meant more for hobbyist computers than for the office. Application programs can access the lowest level functions of the operating system directly if they wish. And this is a double-edged sword. It allows users to write programs that take full advantage of everything DOS has to offer. It also allows for many abuses that can't be eliminated completely because of the 8088 lacking any separation between system and user modes. As a result, the user can do all sorts of things that can cause all kinds of damage, whether deliberately, as in computer viruses, or accidentally, as careless programmers may do. Unix provides a bit more structure than DOS does, but it is still fairly limited. The operating system provides an application programmer interface in the form of system calls. These system calls generally look like function calls in the C programming language. The operating system is modular, with a separate set of functions which interface with the computer's hardware. Some operating systems are called monolithic because it is difficult to discern whatever structure they may have. Interactions can occur, at least in theory, between whatever components it may have, and any procedure can call any other procedure. The name may be something of a misnomer, because such systems must have at least some minimal structure, but this may not be readily apparent. The way in which system calls are invoked illustrates the kind of structure that even monolithic systems have. The user program calls a general system request procedure. This procedure determines the specific service that the user is requesting and then transfers control to that system procedure. This is not terribly different from DOS, where the user loads the function number into the AH register and uses the int instruction to call the appropriate interrupt. The interrupt then determines which function is being called and transfers control to it. This shows that there must be some structure to an operating system, no matter how limited that structure may be. This diagram shows the basic structure hinted at in the previous slide, where we saw the mechanism by which a system call was processed. There is one main procedure that is invoked when a system call is made. This in turn calls the procedure that provides the service that the programmer requested. The lowest levels shown are utility procedures that can be used by the service procedure in doing their assigned tasks. The monolithic system hinted at one possible type of organization, where operating system responsibilities are delegated to different layers. The approach, where different issues are handled by different layers, allows the designer to work at different levels of abstraction when planning system procedures. This approach to handling problems is so sensible that something similar is used in dividing communications problems in a series of 7 layers known as the Open Systems Interconnect model. The lowest layer, layer 0, provides basic multi-programming, so everything above layer 0 sees a series of procedures executed in sequence. Level 1 handled memory management, which consisted of main memory and 512 kilowords of backing store on drum. Backing store is memory contents stored on some external storage device because main memory is too small to handle everything. This all meant that higher layers did not have to worry about memory management. Level 2 handled communication between the operator console and processes. Layer 3 handled input-output devices, so higher layers could deal with I/O as virtual devices, not real devices with various eccentricities. Layers 4 and 5 handled user and operator processes. Dividing up this way simplified system design and implementation far more than the simple structure of monolithic systems. The virtual machine has many advantages of its own. It allowed users to treat a single system of computer hardware as if it were several different machines, including a batch system and a time-sharing system, in whatever combination the user wanted and the load of the processor could handle. The system's virtual machine monitor ran on the computer's bare hardware and created the illusion of multiple computers, each one complete with a set of registers, main memory, and whatever peripheral devices there were for that particular virtual machine. Processes running on different virtual machines had no way to know about each other. The concept of virtual machines is still around, although it serves a different purpose. Virtual machines are used to provide compatibility between operating systems and programs designed to run on different computer platforms. As a result, Windows can run more than one DOS program at once. Macintoshes can run Windows, and so on. For a Mac owner in a PC world, it allows one to run all the popular software that he or she needs without sacrificing the ability to run Macintosh software. Most newer operating systems use a minimal kernel. A user process, the client process, requests a service by sending a request to the appropriate server process. The same model can be easily adapted to create a distributed system over a multiprocessor system or a computer network.